molecules is entropy driven process. It's meaning that the folding and making tertiary structure cause to decreasing entropy and vice versa. And
Yeah.
unfold. Okay, the entropy driven is meaning based.
Entropy driven, it means it's influenced by entropy. So
Mhm.
the chaos and the high energy causes the protein to fold post translation. And then when we break few bonds due to temperature or any other denaturing factor, entropy will go up. So it will cause denaturation.
And when we say that the H bond and the van der Waals and electrostatic interactions are exothermic, it's meaning the breaking of that.
So they are exothermic, meaning if you have heat, the heat will destabilize them.
Mhm.
Heat will destabilize them, and cooling will stabilize them
Okay,
because
yeah.
they're exo. And the opposite is for hydrophobic interaction. They're endothermic. So heat will actually stabilize them because they
Yeah.
suck up heat, and cold will destabilize them. Very good. Any other questions? All right. I have I have three screens here, so I'll try to figure out which screen I need to share. Let's see here. Okay, you guys. What are you? Am I sharing the right screen? Okay. Okay. And then let's see. I want to look at something to bring my computer so that I'm not turned the wrong direction. I'm not set up to teach in my office. Okay, here we go. All right. So I want to make sure that I see everybody. So I'm going to extend my BT. If you're able, do turn on your camera. It's really odd to be teaching with not seeing faces. Only Kevin said he doesn't have a camera in front of him. Maybe or maybe not, it's true. Okay. All right, Kevin, I
I
believe.
can I can grab my laptop if you want.
Well, I would love to see you. Go get your laptop. Am I annoying mother? I am. Okay. So, all right. Let's get started with our regular recap questions. Okay, so define protein denaturation. Who would like to define it in simple terms, and then we'll ask more complex. Andressa still has the participation sheet. Okay.
Yes, I have it.
All right,
Would
you
it be the unfolding of the tertiary structure?
it is
Or
unfolding of the protein in simple terms, but denaturation can occur at the tertiary level. You can also get denaturation at the secondary level. And we can also get denaturation at the primary level when you break peptide bonds. Okay, so you have denaturation at all of the levels can occur. And also, if you have a protein that forms quaternary structure, we don't call it usually denaturation, we call it dissociation of the quaternary structure. Yeah, good. So can you give me an example of when amino acid composition can affect thermal stability and in which direction?
Does it mean that hydrophobic amino acids cause to increase the thermal stability, or for example, cysteine, also the sulfhydryl group has a sulfhydryl group that cause to increase the thermal stability.
Yes, absolutely. So amino acid composition, let's say if we have high hydrophobicity over 30%, so usually plant proteins in nature at higher temperature than whey protein, for example. And also when you have higher SS linkages, higher content of SS linkages, then the thermal denaturation will happen at higher temperature. Another component, the composition of amino acid and the sequence and the formation of secondary structure can impact thermal stability. The more ordered the protein is, the more prone it is to thermal denaturation. Less ordered structures like KCG will denature at higher temperatures, for example. Okay, now how does water facilitate thermal denaturation? So at low concentration versus high concentration, what happens? So with more water, do you have lower denaturation temperature or higher denaturation temperature?
More water causes to lower temperature of denaturation.
Higher temperature, higher moisture, sorry.
Yes, high moisture causes to lower TG or transition glass, and it causes to the denaturation happening lower temperature.
Yeah, you will have lower with higher moisture, lower glass transition. That's one thing, but denaturation is another. So also with higher temperature, you will have lower denaturation. Higher moisture, you have lower denaturation temperature. The water in the system will become thermodynamic, will gain movement, and then will go into the structure of the protein and cause swelling and breakage of some hydrogen bonding with water and enhances the denaturation at lower temperatures.
Oh, I'm sorry, I couldn't understand. The higher water concentration causes to higher denaturation?
Lower denaturation temperature, but more prone to thermal denaturation. The temperature
Yeah, I understand. Yes,
yeah,
yes.
temperature of denaturation would be lower.
Yeah.
Okay. What about protein concentration? Why at high protein concentration we might end up with irreversible denaturation upon heating? What do you think happens after denaturation?
Aggregation?
Shri, tell us. You're in the lab?
Secondary structure.
Oh, okay, go ahead, Howie.
Sorry.
Go
Yeah, protein may reform some secondary structure like beta sheet after denaturation upon heating.
So when you have high protein concentration, yeah, you can form beta sheet intermolecular, so not just intra, so across with different protein. But what else other than hydrogen bonding can happen? At high protein concentration,
Disulfide bond.
disulfide bond, also hydrophobic interaction. So at high protein concentrations, proteins are close in proximity to each other. So interaction is more likely to happen, whether hydrogen bonding by beta sheet formation or hydrophobic interaction. And mostly what makes it really irreversible is strong hydrophobic interactions and disulfide linkages. Yeah. So that's why proteins that have high hydrophobicity, such as eggs, for example, and plant proteins, when the egg white, when you form the gel, the egg white, when you fry the egg, this is irreversible because you have such high hydrophobicity and a lot of sulfhydryls. So that egg white will not be liquefied. All right, so we're going to go talk about factors that influence protein structures. But before we go into that, if you want to think about extrinsic factors, we talked about temperature, but what other extrinsic factors will have a direct bearing or impact on protein structure?
pH,
pH is one. What else?
salts,
Salt. Yes. So pH, salt,
Sugar.
sugar can too. Yeah. What else?
Moisture content.
Moisture content. What else? Physical. What could happen physically? Like think of
high shear rate,
shear. Yeah, okay. So high pressure shear, or if you're kneading even a dough, that's physical stress that you're putting on your proteins cause denaturation, or beating, physical beating of your eggs. So that's what we're going to talk about next, is the different factors that can cause protein structural changes, other than just the thermal changes, thermally induced structural change. So we categorize those factors into physical, and let me put pointer. I want the pen. Yeah, I want the pen. Okay, so we have the physical, where we talked about temperature already, but the force, shear, the pressure, ultrasound, microwave, cold plasma, for example, can fit in this category as well. Later on, we'll talk about modification by components or physical factors like cold plasma. And then we have the chemical, so the pH, the salt, having reducing agents, presence of enzymes, and then organic solutes and solvents. So, and detergent like SDS, organic solutes like urea, for example, organic solvents like hexane. Oh, why is it not moving? There. Okay. So let's talk about pH. So with pH, once you change, there are three different ways, obviously, you can change the pH. First, you can bring the pH to the isoelectric point, or you can increase the pH way above the isoelectric point or way below the isoelectric point. So when you increase the pH up or down, you are really making most of your charges in one direction. So if you go way below the isoelectric point, your protein will be positively charged. So you will have like charges positive. That will cause repulsion. And the repulsion can be within the protein molecule, because within the protein you have charged groups. And if you have a lot of positives, let's say, you will have the amino acids within the one molecule will repel each other. Well, you will have functional group repelling each other, causing unfolding, whether at very low pH or very high pH. So unfolding can occur at extreme pH. So that's because of like charges. And then when we lose charge, meaning net charge, that would be at the isoelectric point. For example, a very common example is the formation of yogurt. That happens when the fermentation happens, the bacteria chews up lactose and convert it to lactic acid, the pH drops. When the pH reaches 4.6, this is the isoelectric point of casein. So the curd forms, and that is a form of gel, but this causes the denaturation. So the unfolding and the formation of gel matrix that traps water. This is mostly reversible if you bring it down the pH to the isoelectric point and don't leave it there for a very long time, then it becomes reversible. What we talked about exposure to stress for the protein, the longer time it is exposed to a particular denaturing condition, the more it becomes irreversible. Now, some pH-driven denaturation is irreversible. So let's say high alkalinity or high acidity, you break some peptide bonds. Once peptide bonds are broken, this is irreversible. Sometimes also even acidity and alkalinity will cause deamidation. So asparagine and glutamine will become aspartic acid and glutamic acid. The presence of these amino acid, glutamic acid and aspartic acid, changes how the intermolecular interactions happen. So within the protein itself, the one molecule, we might get, like charges. So that might cause a little bit of repulsion and denaturation. So that is irreversible. Once you deamidate, you cannot reamidate. It's a covalent bond that we are breaking. So, any questions so far on the pH situation?
I have one question, Pam. I just can't picture how the repulsion of these groups can cause the unfolding. Can you
Okay. So
explain
yes,
that?
remember that image, I think in the second lecture when I was showing you all the interactions that can happen within a peptide, within a polypeptide? Do you remember that image? I can bring it up. Let me just escape here. Doesn't want to escape. Escape. Happened. Like, no discard. All right, so I want to open this other. This one here. So here I was talking about the different interactions that the different residues can form within a protein molecule. So some of it is electrostatic interactions. So when you have amine plus and COO minus, so you have the plus interacting with the minus, correct? And then when you change the ionization status, you lose here under a high, let's say a pH, you lose an amine group here. So not an amine, I mean a proton. And then this is no longer positive, so you lose an ionic interaction. Does that make sense?
Yes, I can
Uh,
see. I can see
Okay,
that.
good. All right. Go back here. All right. So, let's see, did I lose my? Probably I did. That's okay. Okay, so salt is another factor that can cause denaturation. So it depends on the concentration and the type of salt, not just the concentration. The type of salt is very important. So for particular salts, at a low concentration, often less than 1 molar concentration, we have a phenomena that is known as salting in. So with a little bit of salt, the salt is interacting on the surface of the protein loosely, not strongly, and enhancing the charge load in a way that we enhance water interactions. So now with this little bit of salt, we have more protein-water interaction. So we call it salting in because we enhance protein solubility and also stability. So for example, in acidic beverages, you often read on the label phosphates. Phosphates are added to enhance stability. Suchi, you have your hand up. Yes. But you're muted.
No, I was just trying to read the small image. Sorry,
Where? Here?
to distract. Yeah, yes.
You can see?
Yeah. Sorry, I was a little distracted to read that. No, I
Oh,
didn't have question.
Okay, no worries. All right. Okay, so that's salting in. However, at higher protein, not protein, salt concentrations, and also depending on the type of salt, we get another phenomena called salting out. So what that happens is the salt interacts strongly on the surface of the protein. And if they do interact strongly, that is also why sometimes we have a hard time with dialysis to remove all salts, salt concentration, or reduce it to a certain level, because some salt really interact strongly with the protein. And if they interact strongly with the protein, what happens is we have an internal opening up because now we blocked some negative charges here and we also blocked positive charges. So now we cause some ionic interaction to be broken. That's one. Another thing that could happen is salt competing for water. So instead of the water interacting with the protein, now the salt is competing for the water and less interaction with the protein happens. Another thing is the salt components will shield the charges on the protein, also reducing those charged residues on the protein to interact with water. So multiple things can happen. So with shielding the charges, we are altering what we call the hydration properties of the protein because now the protein is interacting less with water. And what happens when the protein interacting less with water, if you remember that crystalline-like structure of the protein around, of the water around the protein, that also will be disrupted, like that ice-like structure. So here it will come back again later, but when salt stabilizes the protein, specific salt at very low concentration, we are actually enhancing protein water interaction. So especially when the salt bind weakly or loosely. However, when the salt binds strongly and there's high concentration, that is a destabilizing force. Okay, so that's what explained what I mentioned, but in words here for you. Here's a demonstration of different salts having different impacts. So here, those structures that are not solid, a filled color, these show us that with high salt concentration, we have high denaturation temperature. So these salts act as stabilizers. So we call them cosmotrope. So they bind loosely and allow more protein water interaction. So structure stabilizers. However, different types of salt acts as destabilizers. We call them K-tropes. So these K-tropes examples, with higher concentration, denaturation temperature decreases. So we see a decrease in temperature, in denaturation temperature with increase in concentration. Examples of stabilizers are sodium phosphate, sodium sulfate, sodium fluoride, and then a bromide, iodide, perchlorate, and thiocyanate are destabilizers. Here, what we're saying is the protein structure is more influenced by the anion than the cation. So the type of anion determines whether the salt is going to be a destabilizer or stabilizer. That's what it meant here. Sugars, small sugars, and another small compound, they act also as cosmotrope. So a little bit of sugar can enhance the stability of the protein and increase the denaturation temperature. Here's an experiment I did with some students at Purdue. I was helping with the food chemistry lab, and we did this small experiment to look at the impact of different factors on the formation of albumin gel from egg white, egg albumin. And the temperature of opalescence, meaning the temperature at which we see cloudiness and start of the formation of the gel. So when we only had water, temperature that we got to opalescence, that means denaturation and formation of those gel, was at 85 degrees C. When we added sodium chloride, the temperature decreased. But when we added ferric chloride, we didn't get denaturation, no matter how we increased the temperature. So what happened is this, the ferric ions formed bonds within the protein and enhanced stability of the protein. When we added sucrose, a little bit of sucrose, 0.01 molar, we didn't see a change. But when we increased the concentration a little bit, the temperature of denaturation increased. That is a stabilization effect. Now, when we added an acid, when we decreased with the 0.01 molar, we got to a pH that is 6.15, closer to the isoelectric point of egg white. That's why the temperature of opalescence decreased, because now we lost a little bit of charge, net charge. So the temperature at which denaturation occurred became lower. When we added a lot more acid, yeah, a lot more acid, the pH was very low. So we had a net positive charge, a high net positive charge. So we didn't get gelation. That wasn't because of the extremity of a repulsion. The protein potentially denatured, but it wouldn't form a gel. Any questions?
I have a question. So before I saw some papers they're talking about the sugar and protein interaction during denaturation. So the term they are using that sugar works as a molecular spacer between the proteins, and that kind of stabilizes it for denaturation.
Yeah, I mean, everybody describes it a little bit different. They call it molecular spacer because now with the sugar interacting loosely, then you don't have protein. It's kind of in the way of protein-protein interaction because you have that sugar interacting loosely. And also, it also enhances protein-water interactions. So when you have protein-water interactions, you have less protein-protein interactions. But everybody uses different fancy terms of explaining this. Yeah.
I have a question about the adding the acid and decreasing the pH around 1 or 2. You said that it's that the denaturation is happened, but gelation is not happened. It's meaning that the solubility increase. Yes, they are soluble while they denature, but they are soluble. Yes.
Because they're soluble, because the fact that there is very high net charge, they're interacting with water, and because they have all very like charges, very high and like charges, there's a lot of repulsion. So these proteins, even though they are denatured, because of that excessive repulsion, they're not able to come together to form a 3D network, which is a gel.
Thank you.
All right, so now moving on to organic solvents. And how does it work? When you have an organic solvent, what happens is the organic solvent solubilizes hydrophobic groups, meaning your hydrophobic group are mostly in the interior of the protein. They're hiding from water in aqueous. But then when you put organic solvent, these hydrophobic residues now want to orient themselves to that organic solvent. And also these hydrophobic interactions within the protein are weakened now because now they want to interact with the solvent rather than interacting with the other hydrophobic groups within that protein. So that causes unfolding, basically. The weakened hydrophobic interactions within the protein causes that unfolding to happen. And then at high concentration of the solvent, we get this solubilization of the nonpolar side chain. And then here's this point, what it's saying, decrease permittivity. It has to do with the interaction, electrostatic interaction or hydrogen bonding with water. When you have less water and more solvent, you have less electrostatic interactions with water. So you have more interactions with non-water material, protein-protein electrostatic interaction, as well as repulsion, because if you have like charges, now there's no water to mediate. So without the water, then we get more repulsion for like charges. So organic solutes, reducing agents, organic solutes, and detergents. So these are also denaturing. So reducing agents like glutathione, beta-mercaptoethanol, DTT, a high amount of cysteine, free cysteine. These are all called reducing agent because what they do is they reduce disulfides into SHs. So these SHs can be oxidized again with oxidizing agents into SS. But the reducing agents will break them off and then cause denaturation and unfolding of the protein, especially if you have disulfide linkages within protein that is adding to the stability of that protein tertiary or even quaternary structure. So glutathione, beta-mercaptoethanol, and DTT are very commonly used reducing agents. Urea is an organic solute, and guanidine hydrochloride is also an organic solute. These two can cause also denaturation by breaking hydrogen bonding. So if you have hydrogen bonding that is stabilizing the protein, these organic solutes break hydrogen bonding and then interact via hydrogen bonding with our protein. So they also cause destructuring of the water as well by breaking hydrogen bonding and forming themselves hydrogen bonding. The last one here is detergent. So sodium didutyl sulfide, we use it also to denature protein. It breaks almost all non-covalent interactions within a protein, causing complete denaturation, irreversible. It binds very strongly with the protein. That's why it's irreversible. And we use it a lot in SDS page, obviously, because it causes all the surface protein to be negatively charged due to the binding of this sodium didutyl sulfate, and all will migrate based on size from negative to positive.
The guanidine HCl doesn't cause to destruction of the hydrophobic bonds too?
It does. Well, the thing is, once one thing starts, mostly hydrogen bonding break, a lot of other interaction follows, because when the unfolding starts to happen, you become your delta G becomes negative, and it becomes a spontaneous denaturation. Then we have denaturation by enzyme, and the most common one, other than breaking the peptide bonds, and you denature the protein at the primary level, a good example that destabilizes casein micelle. So you have the casein micelle that is stabilized by kappa casein on the surface. With these hairy-like structure are the very negatively charged glycomacropeptide. So the rennet chymosin is very specific to cutting a specific peptide that frees these glycomacropeptides, detach them from kappa casein. Then it destabilizes the casein micelle in milk. So you have, caseins are very hydrophobic. So when you lose that stabilizing net negative charge on the surface of the kappa casein, the whole structure breaks. So basically, then you expose hydrophobic groups and they start coming together, forming strong hydrophobic interaction, calcium phosphate bridges across different micelle, as well as, mostly hydrophobic bonding, and also calcium phosphate bridges start happening, and then you form the curd and the whey is expelled. So basically the enzyme caused disruption of that stability of the micelle by breaking that glycomacropeptide that is negatively charged. So that peptide goes into the whey. That's why cheese whey does not only contain whey proteins, it contains the glycomacropeptide. Okay. Then we have the physical denaturation. Who doesn't like to knead dough, for example? Doesn't it give you satisfaction to just like punch this dough? No? Nobody shares this excitement with me? Okay. Well then, so that punching and kneading of that dough is actually denaturing the protein. So the protein opens up, and then you bring gliadins and glutenins align next to each other and then start forming hydrogen bonds. They are prolamins because they're high in prolamine and high in glutamine. So that glutamine is really high, so you have a lot of hydrogen bonding happening. You form the beta sheet, and then they are in close proximity, very convenient to form disulfide linkages. Then the hydrogen bonding brings them together, and then disulfide bonding happens, and also tyrosine linkages. We'll talk about it when we talk about gluten later on. So you have three types of bonding that happens, but what allowed it is the physical denaturation, realignments of these proteins in a way that they can bond and form the viscoelastic gluten. Beating of the egg white also causes denaturation and reorientation of the hydrophobic and hydrophilic parts of the protein, the hydrophobic to the air and the hydrophilic to the aqueous, and then you form this film around air bubbles and the foam, the film of protein around the air bubbles, and then the foam is formed. Yeah, that's exactly describing what I said in terms of the gluten strand formation, mostly induced by hydrogen bonding that facilitates disulfide linkages and tyrosine linkages. We'll talk about that later. But then you form gluten strands. The beating, exposing these hydrophobic residues to the air, and then forming a film around the air bubbles. Okay. This table is good for studying, so it kind of summarizes what we said, how each component or factor that denatures a protein and impacts its structure. It's listed here, and the structural impacts. Here's a good summary table to study from. Lastly here, let's talk about method to assess protein denaturation or degree or extent of protein denaturation, not only whether the protein is denatured or not. So come on, I'm gonna go around the room. Each one of you give me one method. There are enough methods to go around everybody. Now the lucky person will be the first person I ask. And because Kevin went and got his laptop and was a good student, listener to me. All right, you start first, Kevin.
DSC, you can measure how much it's denatured by looking at the change in enthalpy.
Very good. So DSC gives us two terms, the change in enthalpy and delta H, and also the peak denaturation temperature. But sometimes if the protein is denatured, DSC really is not very helpful because it's just going to give me a straight line. All right, let me see. I want to go, Vici, tell me next. What would give you an indication?
Um, can you use SDS page?
Absolutely. You're very right. You can use SDS page. It gives you an indication of polymerization. And if you have polymerization, that means the protein got denatured and formed polymers. So, but sometimes SDS page, if it doesn't show polymers, that doesn't mean that the protein is not denatured. So oftentimes we need multiple assays to look at the extent of denaturation. Very good. Vici, let's go to Miriam.
Size exclusion.
What? Oh, to look at polymerization, right?
Yes, to see
Okay.
the degree of denaturation and the unfolding and everything. I think so.
I think
It
that
should be showed.
it doesn't really tell you the degree of unfolding. It would tell you if the protein formed larger polymers. You will see soluble aggregates formation, for example. So it's kind of like another way to look at molecular weight distribution by looking at polymers. Like you use SDS page, but DSC and size exclusion, you can look at the relative abundance of the different polymers within the system. Okay, Shri, what do you think?
You can use OPA, measure degree of hydrolysis.
Okay, so degree of hydrolysis will tell us a denaturation at primary structure. So basically, if we broke peptide bonds. Okay, what else? Let me see. Who am I gonna ask? Medora.
Okay, I'm gonna throw out PDCAS because that's a very far one, but it can affect denaturation can affect digestibility.
Absolutely, it's not very far one. It's a good one. So yes, protein denaturation, a partial denaturation actually enhances digestibility because enzyme will have access to the binding sites. But polymerization and aggregation will reduce digestibility. So it's an indirect measure of protein denaturation. Andressa, what else do you think would be a good measure? Or indirect or direct?
Can we use FTIR to look at the secondary structure?
Absolutely, IR. So it could be FTIR, it could be Raman. We can look at secondary and tertiary structural changes. It could be NMR too, by looking at changes in the tertiary structure. Very good. There are a couple that are common. How are you? Did Andressa take your thunder of FTIR?
Yes. Maybe we can also measure water holding capacity.
Water holding capacity. You really like that one, don't you? Yes, you could, but it's not one that we go to very often. You could measure water binding capacity because water binding capacity has a has a direct relation to denaturation as well. Okay, but there are a couple more that are in our lab. We kind of like our bread and butter. Suchi, do you wanna give us something?
I think change of surface hydrophobicity can be one.
Yes. Yes, that was one of the two I was looking for. Change in surface hydrophobicity, absolutely, because the protein, when it denatures, it unfolds, so surface hydrophobicity increases, but also when it polymerizes, surface hydrophobicity decreases. So it's a very good one to monitor denaturation and polymerization. Very good. There's one more that it's also bread and butter in our lab.
Can I ask a question
Sure.
about the surface hydrophobicity?
Yeah.
It shows that the denaturation it happened or not, but it shows a degree of denaturation.
No, unless you are monitoring the change in surface hydrophobicity over time at a particular pH and temperature conditions. But like at increments, you actually monitor it and you can calculate the factor. But yeah. There's one more essay I want you guys to tell me. If you tell me, you get a piece of chocolate from me at some point.
Affinity chromatography, can we say?
You know, I'll give you a piece of chocolate, but not the answer.
Could it be zeta potential, Pam?
Zero potential. Okay, surface charge. It's not the one that I was looking at. It doesn't, sometimes it changes in one direction, not the other. So it's not one that we first go to. But well, you can come to me for chocolate, Gertrude, just for courage. Okay, but there
UV visible?
you can do UV vis actually when we are doing surface hydrophobicity, really. Yeah, okay. I think
Is
I'm gonna bring chocolate next time I come, but I'm still not getting the answer.
is it change in solubility?
Yes, there he goes. Okay, he gets 2 pieces of chocolate. Everybody else gets 1. All right. Yes, because solubility, when the protein is denatured, it goes down. And when the protein is polymerized, it goes even more down. Now, there is a caveat with sometimes formation of soluble aggregates helps with the dispersion of the protein in solution. Sometimes heating gives you enhanced solubility because of thermodynamics. So solubility is a good indicator in so many ways. Okay, very good. And here they are. I think everything you said, with the exception of activity, if we have enzymes. If we have enzymes or measuring enzymatic activity, it would tell us if the enzyme is denatured or not. This is IR, specifically surface enhanced Raman spectroscopy. So for whey protein, for example, non-heated and heated, we see a complete spectral change of non-heated to heated. A lot of shifts, formation of new bonds. So we can decipher every peak to see how denaturation impacted all functional groups and interactions. This is our wonderful DSC. This is an old DSC that we used in our lab. It used to have a positive peak. Now the program we have give us the negative peak. But it's basically same. It gives you the change in enthalpy. And also the peak, the onset of denaturation and the peak denaturation temperature. And then SDS page, looking at the formation of polymerization. This example here is whey protein. And we heated it at different, at the same temperature for different intervals of time. And we looked at surface hydrophobicity and the formation of polymers and the reduction in monomers over time. Okay, so this ends our extrinsic factors, a lot of them, that impact protein structure in the form of denaturation. And then now we want to study functional properties. And later on, we will study the impact. Well, while we study functionality, we'll have few examples of impact of structure on function. Okay. All right. So, do you have any questions before I move on to the next one? Any fun facts? What's your favorite functionality testing? And which one you can tell us something about? Okay, I'm gonna go around the room again. I'm tired of talking, you gotta be involved with me. All right, I'm going to go to Anando, because you're here. Tell me a functionality that you know of.
One functional property that I checked for the in my lab is the emulsion capacity.
I can't understand anything you say.
I can try to. Am I audible now?
No, I think I'm gonna skip you. Sorry. As long as you can hear us, that's fine. I'm just going to go to, let's see. How you?
Functionality?
Mm-hmm.
You mean give a
Your favorite one that you always tell me about.
favorite ones?
You just said it.
Water holding capacity, water
What?
binding capacity. Yeah.
Yeah, how do you measure it in your lab?
In our lab, yeah, you mentioned, in fact, we measured the water binding capacity.
Okay, it is a functionality. Tell me about water binding capacity.
Yeah, the first step is to make pea protein isolate powder into suspension, suspension, and then incubate for a while, and then centrifuge the solution, centrifuge the suspension, and decant the supernatant, measured how much water the powder can retain.
Yes, very good. So grams of water per gram of protein. So you can actually report it as grams of water per 1 gram of protein, or you can change it into a percentage as well. Grams of water per 100 grams of protein. So either or. Okay, I'm not gonna go all around the room, but we talked about a lot about different functionality, water binding, oil binding, water holding, solubility, gelation, emulsification, foaming, viscoelasticity, viscosity. These are all functional properties of that we measure for proteins. Other macromolecules can have also viscosity and gelation, but for starch, we call gelatinization, for example. So I'm going to go over all of these functional properties and also describe how the structure of the protein can impact these functional properties.
I have another question, Pam,
Yes.
related to the last slide deck, but is there ever a protein that is like so tightly compact or something like that that a reducing agent isn't able to break all of the disulfide bonds?
Yes. So the problem with the reducing agent is twofold. Reducing agent, there is not one reducing agent that will break all disulfide linkages. That is kind of almost impossible, really. No matter what the concentration is, you have accessibility also of that reducing agent to different sites. We try to put as much of a high concentration as we can in the solution to break as much as we can, especially the quaternary structure. We try to break them up as much as possible so that we can see the monomers go down our gel. So, but sometimes the protein is highly aggregated or highly polymerized. Even with the reducing agent on the gel, you don't see them all go down. You see some at the top, you see some, doesn't go through the oil even. Another issue with reducing agent is that if you have a solution and you put a reducing agent there, sometimes the reducing agent breaks SS and induce something we call disulfide interchange. So depending on the concentration of the reducing agent, you break and form. Because take alpha-lactalbumin, for example. We'll talk about it later. It has how many? Who came to me and asked me about this? It has 4 double disulfide, right? Miriam, I think you're the one. So, but it doesn't have a free sulfider group. Beta-lactoglobulin has free sulfider group. So if you have beta-lactoglobulin and alpha-lactalbumin in your system, whey protein, and you induce that sulfider group acts as a reducing agent. With heat, it breaks some SS and then you form disulfide interchange. And you have a lot of it that is happening between alpha lactalbumin and beta lactoglobulin. Did you know that whey protein gel at 5% protein? It does. I don't know if you knew that. Because our plant proteins, you need, like soy, you need 15%. Pea, you need 20%. But whey, although it's small molecular weight compared to our plant proteins, you have a lot of disulfide interchange that happens and it denatures at low temperatures. So the gelation happens at low protein concentration. I don't know. You asked a question and then I went into an essay of an answer. But did I answer your question, Kevin?
Yeah.
Okay. All right. So let's see. Let's read this and tell me what you think. Before you try to answer, let's define dispersing and dispersed phase in an emulsion so that you can answer this a little better. So if you have oil in water emulsion, so the water is your dispersing phase and the oil is dispersed in the water. What about butter? What is it?
Water in oil.
Water and oil. So you have 20% moisture actually in butter, and it is water in oil, and oil is the dispersing phase, and water is dispersed. Okay. So now try to answer this question.
B and C.
B and C. Yes, correct. So when oil is the dispersing phase, you don't want high hydrophilicity. And the opposite is true. When water is the dispersing phase, high hydrophilicity will be desired because you want to interact with water. And you also want to interact with water not only at the interface, but also in the continuous phase because you want to increase the viscosity to enhance stability. Then globular proteins can form thick films at the oil-water interface. They tend to form thinner adsorbed layer. They can impart extended emulsion stability. All right, so I'm going to draw something. Where is my point interaction. So let's say you have whey protein. They are globular. Ah, that's not what I wanted. Scratch that. This is the first time I tried to draw with this. Okay, let's have your, why is it doing this to me? All right, forget this line. And then you're forming a film around your air bubble. So these are denatured whey proteins. They still have some globular structure, but not completely open. And then you have your casein, open structure. I don't know why it wants to give me a peak. Forget that peak. This is really bad, but you get the point. So your casein molecules are spread out. Which of these two will form a thicker film, the casein or the whey?
Casein. Thicker. Thicker.
Thicker.
Thicker. I think. What's that? Whey protein.
Whey protein. So here there's 1, 2, 3, 4, 5, 6, 7 molecules. Here you have 1, 2, 3, 4, 5. So depending on the oil droplet and the homogenization, smaller proteins and more compact in structure you will have more of them at the interface, and then you will form a thicker film. Whereas the open structure are natural emulsifier, they quickly can orient themselves and at the interface and form really good emulsion at low concentration. That's why in our lab, when we measure EC, actually you need only 0.5% protein when we're doing casein, and you need 2% protein when we're trying to form an emulsion with P. So at lower concentration, you can actually form nice emulsion, but those compact, thick, that forms thick film because you have more molecules at the interface. The thicker film contribute to emulsion stability. So with thicker films, you have more repulsion between two oil droplets with the proteins on the surface. So you have less chance of fluctuation and coalescence and emulsion break, basically. Okay. All right, so we're going to talk about all of the different functionality. This is the definition of functional property, which is physical chemical property that affects processing and behavior in food system, the way they're judged by quality attributes. So it's a fancy definition, basically. But this is the actual definition of a protein functionality. So a gel, the behavior of the protein to form a gel that will impact the textural properties that we can see and evaluate. Okay. What are they influenced by? Each functional property is influenced by a combination of factors. And we have usually an interaction between these factors. So the protein composition, amino acid composition, the structure of the protein, configuration or conformation of the protein, physicochemical properties that include surface properties of the protein, the functional groups, ionizable groups, other food components in the system. So do I have sugars in the system? Do I have starch in the system? The water concentration, the salt concentration, the acid concentration. and the nature of the environment, which includes the pH and the ionic strength and the temperature. So really, functional property is such a sensitive property that is influenced by a lot of different factors, basically, is what we're saying here. This is a table that summarizes how the general property and what is the functional term. So, for example, hydration is a general property, but then with hydration, we have solubility, dispersibility, wettability, water absorption, even gelling is protein water interactions involved in gelling. So any functional properties that involve water can be under this general property. Surface property, then for surface property, you have emulsification, you have foaming, you have oil binding or water binding, flavor binding. And then you have the structural, textural, and rheological. So viscosity, viscoelasticity, dough formation, extrudability, all of these terms. And then there's the other enzymatic modification properties. Yeah. So this is a good table to study from as well. This is a table I have from an old book on proteins that I have, really old book, but I really like it. Although it is so old that the protein types are mostly animal. We only have like cereal proteins. We don't even have soy protein here in the protein type. But what I like about it is, forget about the protein type for a minute. It talks about the function, the mechanism, and then what food this functionality is important in. So what's gelation? Water entrapment, immobilization of water, and formation of network. That's the mechanism of gelation. Where is it important? In meat, gels, gel systems, cakes, bakery products, cheese, yogurt even is a gel, candy, like jelly, beans. So that's why I like this table, because it explains the mechanism of each function and where it is relevant, and gives you an example of the protein ingredient that would be good for that function. Later on, we will know that others, of course, plant proteins can have these function and can be used in different food products. So functional properties can be grouped into two main categories. So we have the hydrodynamic aggregation group, and then we have the surface activity that is heavily reliant on surface hydrophobicity. So the hydrodynamic / aggregation, it's protein water interactions, and then also it's protein water protein interactions. So water is there. Because water is there, it falls under the hydrodynamic. So anything that involves water, it is a hydrodynamic functionality. Solubility, water binding, viscosity, elasticity, gelation, coagulation, water holding capacity. Now, the surface activity is emulsification, foam, oil binding, flavor binding. So a lot of characteristics and factors impact each functionality, but mainly size of the protein and the configuration of the protein impact viscosity, elasticity, gelation, and texturization. Mainly, but that doesn't mean that gelation, viscosity are not impacted by surface properties, for example. And then surface properties, hydrophobicity, hydrophilicity, polarity, or one with charge or charge. Hydrophilicity does not only mean charge. So these govern mostly the rest of the functionalities. But that doesn't mean that one doesn't impact. So it doesn't mean surface properties doesn't impact gelation, for example. But mainly size and configuration impact these four characteristics or functionalities, and the surface properties impact those other ones.
The configuration is meaning for example, the amino acid sequence, or it has a secondary, tertiary, or quaternary
Configuration, yeah, configuration or conformation, they're sometimes used interchangeably, but it is the structure of the, tertiary structure of the protein, whether or not also they form quaternary structure. Yeah, so the conformation of the protein shape. Yeah. So I'm going to start with the water protein interactions. And you all like isotherms, right? Isotherm is the relationship of the moisture content. Usually it is reported as grams of water per grams of solids. So it's kind of like moisture on a dry basis. And then the relationship of the moisture content to water activity. And you have your isotherms, and then you have three main regions. And I'm going to explain protein-water interactions in those three main regions of the isotherms. So region 1, when water activity is between 0 to 0.25, this is below the monolayer for most systems, okay? So under the monolayer, the interactions with water are very strong. So if you have water and the water activity is below the monolayer, that means this water is bound by hydrophilic, charged, and polar groups mostly. And they're strongly bound by dipole and hydrogen bonding. So they are bonded strongly. And this water here is unfreezable. You cannot freeze that water, and requires a lot of energy and heat to evaporate it, basically. It's not something that will evaporate easily under regular conditions of evaporating water. And also this region is not available for chemical reactions. Okay. Good. So the second region, we are now starting to form the monolayer. A lot of region with the monolayer can be mostly between 0.25 and 0.4. And as we go above that, we complete the monolayer and we start to form the secondary structures, the second layer of water, the third layer, and so on. So it is available as solvent for low molecular weight solutes and chemical reactions. And then the last region is the multi-layer water. So this is mostly water available for chemical reactions and kind of sort of free water. So what does this have to relate to proteins? So at the monolayer or below, the water is associated with the surface of the protein. So they are chemically interacting with the protein via dipole, and hydrogen bonding. It has different properties than free water. And then we have the entrapped water. So we have the strongly bound water, we have the monolayer water, and then we have the entrapped water, which is basically entrapped in the structure, not necessarily directly interacting. So it is within the structure matrix of that protein. And then we have the free water that is not trapped, flows freely. So when we measure water binding capacity, we're really looking at the amount of water that is retained by a protein under defined conditions, meaning at a specific pH and at a specific salt concentration, let's say. So, and it's measured grams per gram or grams per 100 grams. So the composition of the protein impacts water binding, with the charged amino acid binding the most water. The polar comes next, polar and not charged. And then hydrophobic amino acids still bind a small amount of water, because hydrophobic amino acids do have other groups that can form hydrogen bonding. This is kind of the function of the water bound based on the amount of charged residue. So it has a factor of 1. The polar amino acid they're not charged, factor of 0.4. And then non-polar residue hydrophobic has a factor of 0.2. So they do bind, but not to the extent of the polar and charge, basically. That's the relationship of water binding to the different residues of amino acid. So the factors other than composition, conformation. So you would think that a denatured protein will bind less water. Actually, it will bind a little more water, because now other groups are exposed. So whatever was on the surface and binding, now we're exposing additional groups, and they also can bind water. Temperature. So temperature impacts binding to a certain extent. So if you increase temperature slightly, you increase thermodynamics, so you can bind a little bit more water. But if you increase temperature to an extent of not only denaturation, but also polymerization, you might reduce the binding. pH, definitely, if you increase ionizer of a group, you increase the binding by 2 to 3 times even. Salt concentration, there's again the same with solubility. Here, are you increasing the charge load on the protein, like salting in versus salting out? So that's kind of the same impact. And having little small molecular weight sugars, again, increase the load on the protein and interaction with water, and enhances binding of water. Again, the same concept of cosmotrope, enhancing water interaction, versus K-trope, they destabilize and reduce water interactions. This is and from an old source, I think one of my books as well, but there's a mistake. This should be SPI. This is I. Okay. So this is very interesting. So if you look at soy protein, it starts denaturing above 70, 75, sometimes 80 as well, depending on the source of the protein. So you can see that with increase in temperature, we increase in water binding, first of all, thermodynamics and the start of the denaturation. And then there is a decrease because we are inducing polymerization. So we see less water binding. If you look at casein, why is it hardly changing? Why do you think? It's not really, casein is not really impacted by temperature very much. It's a very unordered structure. Whereas whey protein, you see an increase after denaturation and then it plateaus. It should drop if they measured it for longer time, it will drop eventually due to polymerization. Dear, don't worry about the breast versus thigh. That's not our point here. The point here is the salt effect on meat protein. With higher salt concentration, we see an increase in water binding, but they should have continued to show us a decrease, but they didn't. It will decrease at some point when you increase the concentration to a point equivalent to salting out. The effect of pH, it's similar to water. It has this bell shape where when you have charge, you have more binding. And as you reduce the charge when you're close to the isoelectric point, you bind less. And as you increase the charge, you start binding more. And why is at higher pH here more binding than at acidic pH? Remember that bit from first couple of lectures? So you have tyrosine, for example, has OH. It gets ionized at alkaline. Even sometimes cysteine SH gets ionized at higher temperatures, higher pHs. So you get even more ionization other than your COO, other than the carboxyl groups. Okay, so with more ionization, more binding of water. Okay, tell me the difference between water binding and water holding. I know we mentioned it multiple times. You know it. So I know you're tired. Let's see. What is it? We still have a little bit of time. So what's the difference between water binding and water holding? Which I didn't talk about water holding. It's coming later, but from what I said already.
Water holding is kind of loosely bound, which is kind of 3D structure, entrapping the water.
Entrapping
Water
water.
binding is with the amino acid.
Yeah. Water holding, you are actually holding the water entrapped in a 3D matrix. So it is not, it's loosely bound. It's not strongly bound as the water bound, which we measure by water binding. How do we measure water holding is you form a gel and you apply force and see if you'll get syneresis. Okay, so we'll talk more about how we measure it later. So I'm gonna move into the solubility, and the solubility is the most important functional property, if I say so myself. If the protein is not soluble, you really can't get it to form a gel. You cannot get it to emulsify. It might form be good for texturization though. Like gluten protein at pH 7 is not soluble, but it texturizes really well. So it's not like absolutely useless if it's not soluble. But not every insoluble protein can be texturized. Take protein, pea protein from a commercial source. It's really not very soluble. It can disperse, but then it falls out of solution because of the large aggregates. And these large aggregates, we cannot do anything with them, even they don't texturize very well because they're already formed in a way that if you think about extrusion, the protein goes through your extruder and get the pressure and the temperature, so bonds break and bonds form, and then you form that fibers. But if you have a very large molecular weight aggregated protein, it's very hard to restructure. So poor solubility is not always means that you're going to get good texturization properties. So that means if the protein is soluble, you can work with it in so many ways. It can be an index of denaturation. We talked about that because solubility is reduced with denaturation and polymerization. And it's very much dependent on environmental conditions, such as salt, and ionic strength, pH, and temperature. Okay. So the higher the hydrophobicity of a protein, the lower is the solubility, which is very kind of natural and obvious. And with more charge, more interaction with water, so more soluble. Both surface hydrophobicity and surface hydrophilicity have a direct bearing on the protein. So, for example, the protein can have a high surface hydrophobicity, but if it has a high charge, the protein can still be soluble. Soy protein, for example, if it's not fully denatured and polymerized, pretty good solubility at pH 7. Although it has very high surface hydrophobicity, it still carries a lot of charge at pH 7 when it's not denatured. So both have a direct bearing, hydrophobicity on the surface and hydrophilicity and charge. They have a direct bearing on solubility. And then we come back to that salting in. It here demonstrates how salting in works a little bit. So we're adding charge load, and this charge load not only helps with protein-water interaction, that little bit of charge load, if you have protein-protein interaction via ionic interactions, the negative interacting with the positives on the protein, having this charge here, it's going to reduce the attraction between the proteins, and that enhanced charge load is going to enhance interaction with protein. So we enhance solubility. And salting out does the opposite by increasing the charge load so much on the protein, shielding the protein charge, competing for water, and preventing protein-water interactions. So I didn't want to spend more time on it because I already talked about it before. And then the pH, obviously, at the isoelectric point, the protein carries zero net charge. So you lose that repulsion between the proteins, among the proteins. You lose that repulsion. And if you have hydrophobicity on the surface, the proteins now not repelling each other. They're going to be attracted via hydrophobic interactions. And also with having net charge, you're going to have ionic interactions as well, and then precipitation of the protein. At above the pi, you gain positive charge. At below the pi, you gain negative charge, and then the repulsion and more interaction with water. This is an interesting phenomena that I always bring up to show the uniqueness of different proteins. They don't all follow one direction. So whey protein is soluble at the isoelectric point. Look at this whey protein, not heated, so native, not denatured. No matter what the pH is, it remains soluble. Does that mean it does not have an isoelectric point? Does whey protein not have an isoelectric point? Does any protein not have an isoelectric point? No. Every protein has an isoelectric point. What makes whey protein soluble? Think. Now I'm going to give a chocolate. Scratch all the chocolates I gave out. And now is the chocolate test. What? Now you're going to give me chocolate. All right. Nothing? You got nothing? Is whey protein hydrophobic on the surface, have high hydrophobicity, or has low hydrophobicity, you think?
Low hydrophobicity.
Thank you, Vici. Appreciate that. So very low, actually, compared to plant proteins. So it has very low hydrophobicity on the surface. So what did I say a minute ago? When you have at the isoelectric point, you don't have any more repulsion. What brings the proteins strongly to each other? Hydrophobic interactions. So now you don't have charge, no repulsion. So the other strong force is hydrophobic attraction. So when whey protein has no charge, it has very low surface hydrophobicity. So you don't have that strong pull that brings the protein together. It remains highly soluble. What happens when we heat it at 70 degrees? What did we do to the protein?
Unfolding and denaturation.
Denatured whey protein starts denatured at 60 until 73. All of the whey proteins are denatured. So what happens now, it's unfolded. Now we have hydrophobicity. So if we don't have repulsion and we bring down the pH to the isoelectric point and denatured protein, they're going to aggregate and precipitate. So whey protein, when it's denatured, it loses solubility around its isoelectric point, which is also 4.5, 4.6, similar to casein. But that's why during cheese making, whey protein remains soluble. It has the same isoelectric point, but it is so hydrophilic on the surface. The caseins form curd, form the gel where the whey protein remains soluble. This is soy protein, and all of the plant proteins in general, they have this bell shape. And not only a bell shape, a very, very wide bell shape with very low solubility over a really wide range of pH. Not sharp like whey, like just goes down and then up. Why? Because plant proteins are governed by hydrophobic interactions. They have a really high percentage of hydrophobic amino acids, above 30%, most of them. Total hydrophobic interaction, hydrophobic amino acid residues. So when you reduce the pH, the pH down close to the isoelectric point, you have very low charge, but very high hydrophobicity. So hydrophobicity interactions govern. So you have really poor solubilities. That's, even when you are formulating at pH 3 or 3.4 for beverages, you are still at low solubility for these proteins. So they have really poor solubility here. And the higher the concentration that you try to put in solution, the worse is the solubility because of those hydrophobic drive and interactions. So, and this is demonstrate what I just said when we try to make a beverage at 3.4 or 3. And this is 5% protein. Whey protein remains very soluble. And then soy and pea, very poor solubility at pH 3.4. So this is pH 3.4 for whey right there, right? So it's very soluble. Whereas soy and pea, this is it here, less than 20%. Okay. So often we need to add stabilizers during formulation of beverages when we have plant protein. So adding stabilizers like carrageenan for pH 7 beverages and also for acidic beverages, pectates. Yeah, salt, pectic salt, or whatever it's called, for acidic beverages to stabilize the protein, plant protein beverage. So here is a demonstration of whey protein, regular whey protein. You have excellent solubility around all pHs with a slight dip at the isoelectric point. And then when we heat it, drops out of solution. So this is again 5% protein solutions. Now, one thing we looked at, pH 4.5, is it acidic beverage? What about pH 5.5? Would you treat a beverage at 4.5 as acidic? Would you treat a beverage at 5.5 as acidic in terms of pasteurization? You tell me. Is 5.5 treated as an acidic beverage?
No, I don't think so.
No. So pasteurization to have lower temperature time combination for acidic foods, it has to be 4.6 or lower. So why is this relevant in protein beverages? Because high treatment of acidic protein beverage, what do you get? You really get astringency and a lot of sourness too, because to make the protein solution acidic, you have to put a lot of acid because proteins are buffers. So you end up putting a lot of acid to get to that pH 3.4. So it's very acidic. So acidic and astringent. But if we try to increase the pH to 4.5 to make it less acidic, but still pasteurize under the same condition, protein drops out of solution. It's not soluble because it's isoelectric point. So what we tried in this study is to glycate the protein using Maillard reaction. And then we looked at solubility at all pHs. Glycation resisted protein denaturation, it resisted unfolding. It gave stability to the protein, reduced its isoelectric point, and caused the protein to remain 90% soluble compared to 3 or 4% soluble. So we can make beverages at this pH now, and the beverages can be less astringent and less sour. We only have one problem. What is our problem, Andressa? Why is there no glycated whey protein on the market?
Would it be the color change?
No, with the Maillard-induced glycation, we control the reaction so that we only get the Amadori compound. What are you trying to do, Andressa, right now with you? What is your work? What are you trying to do compared to what Ali did? Ali S.
Scale up.
Scaling. This worked great on bench. We were able to enhance everything. It was wonderful. It's not an easy process to scale for an ingredient production without increasing cost and trying to figure out processing and purification. So it was wonderful. We did this in 2013 on whey, and we are still trying to scale this process. Okay. We looked at, we tried to understand why we saw this enhancement in solubility at this pH. So we looked at surface hydrophobicity for the glycated whey protein and for whey protein isolate. We saw that whey protein isolate, when we heat it at 75 degrees over time, we kept increasing the surface hydrophobicity, and then we decreased due to polymerization. Whereas with glycated protein, surface hydrophobicity to start was lower. It increased a little bit and plateaued, did not increase. So that gave us an indication that the protein resisted denaturing, and that's why it remained soluble at this isoelectric point. So even though we brought it to the isoelectric point, it wasn't completely denatured. We didn't have enough surface hydrophobicity to bring that protein together. And we also measured the isoelectric point, and we saw a drop in the isoelectric point because glycation blocks positive amine. So we increased the net negative charge on the protein, and that's why the isoelectric point decreased compared to regular way. So we try to, understand what happened. Why did we see that much enhancement in functionality? Last thing I'm going to talk about is the impact of both pH and salt on solubility. So this is here salt concentration. And let's think of pH 2 and pH 1 as when pH 1 has more charge. So it doesn't matter if it is acidic or basic. The direction doesn't matter as long as pH 1 will cause the protein to carry more charge compared to pH 2. So what happens here, at the same salt concentration, the pH that gives the protein more charge will have higher solubility. So this compared to this solubility, compared to this solubility. See my point? So the same salt concentration will have different impact on the protein solubility depending on the pH of the system. Okay. The closer we are to the isoelectric point, let's assume this pH is closer to the isoelectric point, the lowest the solubility is at the same concentration. So we always have this relationship between the pH and salt. So basically here, the charger stabilizes the protein. So at the pH that where your protein carries the higher charge, the more stability you have and the more solubility you have. And the more water interaction. And also the more charge on the surface, the higher is the temperature of denaturation. Okay. All right. So I will stop here and I will record for you guys the last bit, and we'll send you an email when I have it recorded. Okay. And if the recording is close to 50 minutes, after the exam, you can go. We won't have a lecture. All right, so that you don't feel like I'm over lecturing. Okay. All right, you guys. Well, happy snow day, and I will see you after the spring break. Bye-bye.
Thank you.
Bye. Thanks, Pam.
Thank you.
Bye.
Thank you.
Bye.